those of you who have gotten to problem 16 will see in the solution that something's not right. And the calculations, I think, are right, but the what do you call it? The symbol here should be bubble point pressure and not convergence pressure, because the bubble point is what we're solving for, and the correct answer is about 1375 psi, but the convergence pressure has actually been fixed at 2000 psi, so sorry about that. Okay, I'm going to save this file. I don't know if it'll save the annotation, but okay. Did we anybody double check the numbers? 22 times the value. Okay, and if we go to $10 per 1,000 standard cubic feet per MCF, then a factor of 3 different, so it's still a factor of 7, 8. It's a big chunk of money, even if you have a high gas price. So it's an important factor, and that's why a lot of money is often spent trying to process out as much as possible for these C3 to C7 components, making sure they get as much as possible into the oil.
So, with technology and stuff like that evolving, and LNG will make it possible to transport gas all around the world, and we have, do you think that the price of gas will be higher?
The comment is that gas is now more international. It used to be that you could only sell gas where you could pipe it, and but now you can ship it. You can liquefy it and ship it in tankers, and that's being done, for example, from Qatar, which has the world's largest gas field, the North Field. And the prices, of course, have to be justified in order. You have to do the cooling, which is expensive, and then you have the transportation. So the point is that I guess that we have a more international gas market now than we used to, which is true. I don't know about international gas price-like things. I mean, I think the big gas development in the United States has had a huge impact on gas prices domestically. Things are changing. I mean, the transport of natural gas in tankers, the development of these shale gas reservoirs, so prices are changing. There's getting more and more gas availability, so its price in general should go down. I mean, because of that. It's a cleaner fuel with regard to environmental issues, so, but it's just one piece of the big puzzle of demand. You have coal and gas, and so there's lots of issues. It's not my subject, so I'm not sure what to say. So
my question really is oil always going to be better?
Yes. I'm quite sure that'll be the case. There are so many other products you can get out of oil that you can't get out of natural gas without a lot of money. Gasoline for cars, diesel for trucks, these things you can't get from natural gas. If all the cars in the world stopped using gas and gasoline and diesel, then things would be different. But I think, these are things I don't really know about in any great detail. But calculating the value difference, that we can do. So, okay, so then I'm going to show you a traditional, conventional, if you will, multi-stage separator process. I think we may have already talked about it, but multi-stage separator process. And this is the kind that's typically used for engineering calculations it reflects either quite accurately or approximately the actual process of even very complicated offshore large field processes. So I'm just going to sketch it. We've got my separator here. This is the first stage. So this is we've got the temperature, pressure are controlled. And then we remove the gas here. And for the kind of process that we use in petroleum engineering, reservoir production and so forth, we generally don't try to extract more of these components out of the gas and back into the liquid. In reality, we often do that, but now I'm not going to do that because we generally don't take that into account. So then we take this oil coming out of the first stage separator into a new separator. And it's at maybe a higher or lower temperature, almost always a lower pressure, and there'll be gas coming off of that separator as well. And then we'll take it finally to a what's referred to as a stock tank condition. In this case, the separator pressure of the third stage is, I'm just going to make it equal to 60 degrees Fahrenheit. It might be a little bit different, and then you correct, but then this third stage pressure, I'm going to say, is equal to the atmospheric pressure, 1 atmosphere. And we end up with this final stock tank oil that we can sell. And there'll be, a little bit more gas that comes off of that separation. So we've got and in general, what we do is that we just collect these gases together. The first thing we do with the gas is that we'll have the number of moles of gas first from the first stage. We immediately convert that to a surface gas volume, standard cubic meter, standard cubic feet. We almost never work with gas volumes at pressure and temperature unless it's down in the reservoir. At the surface, once it gets to the surface, we always convert the metered amount, mass or mole of gas here. It's probably metered in actually in mass. And we'll basically get our standard cubic feet of gas. I don't know why I wrote stage 3. 1. And again, we'll have the same quantities, mass of gas at the second stage, moles of gas at the second stage, and the volume expressed as the second stage, and likewise for the last. Okay. And then we'll typically say that the total gas volume from the well is just the sum of those three. And here we get the stock tank oil volume. We keep track of how many moles of oil we have at each separator. Moles of oil at the first stage, moles of oil at the second stage, and the final moles of stock tank oil. And likewise mass, because we will know the density of that, and we'll have to measure or estimate the molecular weight to make these conversions from moles to mass to volume. Coming into this is some number of moles in, I'll just write it as capital N, with some composition Zi. So this is mole fractions. It's saying that out of the total moles, how much is component I. When we make these calculations, in addition to knowing the moles of oil and gas at stage 1, we will also be calculating the mole fraction, stage 1, in the oil and the mole fraction of stage 1 in the gas. Likewise for the other stages. In the book, it probably is written like this. I don't know. It doesn't really matter. Okay? Now, what this involves doing is making 3 flash calculations, like we're doing in the problems 15 or whatever it was in the book. So we're applying the so-called, these guys that I'm not really happy with. We call it Ratchford Rice, even though they stole it from Muscat and McDowell. Basically what we'll call flash calculation. And the flash calculation is very simply that you know the mole fraction and you know the pressure and temperature. From these two, you're able to estimate K values. Okay? Maybe also the composition is involved through the convergence pressure. But basically what we have to have is mole fraction and K values. And from that, we can calculate the so-called FV, which is just the moles of gas to the total moles. And we calculate the equilibrium compositions. So let's just kind of identify, do we know the information that each of these 3 flash conditions that kind of tell us what we need to know here? Well, coming in, we know this composition. We know the pressure and temperature, so that we're able to get an estimate of the K values from this Wilson type equation. That allows us to calculate, if we say that N, for example, is equal to 1, what we go in with, then this would end up being what? FV, right? The fraction of what comes in that is vapor or gas. So the Ratchford Rice would give us this. I'll make these in different colors, what we calculate. Pink. We get that. We get the composition of oil and gas. That's what we're calculating. Going in with this information. But the next flash calculation is here at TSEP and PSEP2. So now this is called, I need a little bit of room here, so I'm going to what's going into the second separator, we referred to these as feeds. This is the first feed. ZI is the feed into a separator. Okay? So the first feed is here. And this is the second feed, which in our calculations in all the equations, we always call ZI, right? That's what we call the feed. So you're going to get confused here, because what came out of the first calculation as X of I becomes ZI, or the feed to the next calculation, right? So the feed number 2 is equal to the resulting oil composition from number 1. The oil from the first stage is feeding into the second stage. Likewise, whoa, we lost some things down here. It was like, say P and 3. Okay. So this feed, ZI into the third stage, is equal to the oil composition leaving the second stage. So that's
the tree number is supposed to be a standard condition.
the ZI.
P as 3 condition.
Oh yeah, sorry. Yeah, that's that was a C, not a okay. Standard conditions. Yeah, give me a break. There you go. Okay. So it's like bookkeeping. Okay, we have a flash calculation. You go into with ZI and pressure and temperature. You estimate KIs, and then you solve the flash calculation. You get FV and these compositions here. Okay. But now this thing here, is that the vapor fraction? Colors. Is that the vapor fraction from the second flash calculation? The moles of gas in the second stage here, because we need moles to calculate volume. But the moles of gas in the second stage, is that equal to what we call vapor fraction in the Ratchford-Rice equation? No, because in the Ratchford-Rice equation, you're saying you have 1 mole going in as feed. Okay? But in reality, what we have is, at this point here, we have NO1 moles as how much going into the second stage separator. So the accounting is going to be something like this. NG2 is equal to NO1, which is the feed to the second stage separation, times the vapor fraction from the second stage calculation. So this should have been a question mark here. What is this? Okay. That's the feed moles into stage 2. Of what comes in, the fraction that becomes vapor or gas from the Ratchford rice, that's given here. Okay?
Should you sum also the gas that's coming from the first stage?
Not yet, not yet. We're going to do them individually, and then we'll add them together later.
But at the point where you show it there, it's mixed with the previous gas. Like if you take in the diagram,
Okay, I'm lost. We're talking about NG2?
yes, but if you take it from, you have you drew a purple line there, and that purple line is already with the mixed gas from
Here.
the first stage. Where you put the question mark.
Oh, okay, okay. Yeah, no, these are, yeah, these are, yeah. No, NG2 is just only what's coming off of the second stage. Yeah, yeah, it is kind of misleading. And then for the NG3, that's the feed going in is NO2, right? Times vapor fraction from the third flash calculation. But NO2 is equal to NO1 times the, well, it's, yeah, this is correct. So this is correct. But then what you can find out is the following: that NG2 will be 1 minus FV from the first stage, because that is how many moles we end up with in the first stage. Times FV in the second stage. And then NG3 will be this is the oil coming out of the first stage times the oil coming out of the second stage times the final vapor fraction of the third stage. If you do the algebra, I think you'll find this is correct. So effectively, this is and we've assumed that there's 1 mole going in here. So if you had a, if you had 6,000 kilogram moles, you just multiply these numbers by the total moles. But this is assuming we go in with N of 1. So this, if you will, this NG2 have I done this wrong? Maybe I have. Okay, this is the oil coming from the first stage, and then it's flashed into that. There's the oil from the first stage. That gives us the oil of the second stage. I think this is right. Yeah. So the oil that's this. Oil from the second stage is like that. And then the oil from the third stage would be 1 minus I think that's right. And just to repeat, the first stage mole is just FV1. I didn't really derive this, but I think it's right. So when you do these calculations in the new assignment after you finish the first assignment, and we're going to do the multi-stage flash calculation, you kind of have to, this is the bookkeeping, okay? This is our bookkeeping. Of moles, okay? All right, any questions? Now, at the end of the day, we'd like to have some way to assess how efficiently we're extracting these intermediate components, C3 to C7, into the oil. We'd like to have some visual of that so you can take it home on the weekend and show the folks, okay? Something they understand. And or even yourself to understand it. All right, so there's a way that we often use to summarize the overall efficiency of this whole process. You take the whole process and you end up with the total gas out and the total oil out. Okay, so, and irregardless of what's inside it, because we may not be doing the calculation, someone else is doing it in a much more complicated way. But we're still doing it on a component basis. And so what we end up with that's of interest and important is really this quantity here, right? Because that number there is what we're getting 20 times, at least for the one component, but for all the components, it'll be around at least 20 times more the value having that component down here than having it up here. Okay? This has got this 20 times the value. So one metric that you can understand is that if I say that for all these components, 3 through 7, I'm getting a certain efficiency of recovery of C3 into the oil. In other words, for every kilogram of C3 entering my process, I'm getting a 30% efficiency. 30% of those moles I'm able to keep down in the oil. That you can understand, right? Because you know you're making 20 times more bucks with it down there than the 70% that ends up in the gas. Mentally, you can compute that you're making more money. You can understand that. For the C4, it's 45% more efficient. We're getting 45% efficiency, extraction in the oil. For C5, it's 75%. For C6, it's maybe 86%. For C7, 93%. Okay? And for C7, you think 93% is good. Well, you should be think of the money we're losing on the 7% that's still in the gas. Okay? So this efficiency factor is a number that we often use both conceptually and computationally in our models. So we're going to define a component stock tank oil recovery factor. Which I'm going to call R recovery factor stock tank oil component. There you go. It's got all the words in it. And what are we going to define that as? We're going to say that out of all of the moles of that component that come in the feed into our process, 1, 2, 3, 4 kilogram moles for iso C4, right? 1,234 kilogram moles of this iso C4 coming into our process. What percentage ends up as this 22 times more valuable? That is basically it's this number here, which we basically calculate by taking this times the final stage 3 oil. Okay? Times 100 to get percent. And then graphically, it's very nice and easy and convenient to plot this C1, C2, C3, I'm getting lazy, C4, C5, C6, and C7, and maybe I'll just put all of the C7 together, right, or something like that. I'm getting a bit lazy. Go ahead and do it. Since we talked about this, I'm just going to do it that way. So here we're going to go from 0 to 100% recovery factor in the stock tank oil of a given component. And these are the components I. And what you're going to get, something is a bar chart. Actually, that's probably too high for ethane. And then it's going to get pretty high up here. And what we want to do is that we want to compare this one, which is our single stage flash, for example. That's the most inefficient way of doing the processing, with a more optimal separator process. Okay? And make the comparison. How far can I bring this up by doing a multi-stage process? Okay? Lots of money to be made. Okay? That's with the multi-stage flash process And what you would like to have is some kind of optimal conditions of these three stages. Well, you only have two stages you can control. Probably the first stage is all you can do much with. With optimal separator pressure and temperature, and let's just say of the first stage, I can pick and choose the pressure and temperature of the first stage, and I want to get a maximum stock tank oil volume. I want to maximize this by changing these two guys here. For example, you could change all four, but that is the reason Muscat and McDowell wrote the paper in 1949, is to do things like this, to get the most money out of a well stream. But I think what's equally important and interesting to see is how that extra oil that we're getting by the multi-stage optimal process, how it's changing this recovery efficiency for each component. Because you don't have it, you know, I'm putting bar charts here just out of my, you know, what does Curtis know? You know, is it actually 5% here, or is it 0.5%? You know, this is cartoon. And it'd be interesting to see what is the efficiency of a single stage flash for propane. How inefficient is it really? So anyway, this is going to be our assignment too. Okay. I think I'm out of ideas for, let's see here. If there's anything I've forgotten that should be there.
Is there a reason why you don't put an arrow C1, or isn't it possible to
I don't think so. For practical purposes, I think the amount's so small. The other thing is that this final oil has to be what they call stable at the end of the day, and it needs to it shouldn't be too volatile or flukty. I think. Yeah, I mean, the oil needs to be stable, so you can put it in a tank or a tanker, and it doesn't evaporate a lot in transportation. So there's some criteria. The more methane that gets in there, the less stable it becomes. So there's actually there's kind of an advantage to keeping the methane and probably the ethane as low as possible, but getting to help get as much as the C3 and heavier. I think that's right. But if you only can use multi-stage separation like this, pressure and temperature, you don't have much control of that. So I don't think you want actually the methane in the stock tank oil. It's not really my area, but I don't think so. Okay. That's a good question. Okay. Anything else that's real unclear before we break? Important questions like who's Green Bay going to play this weekend, or American football.
How can this curve change if you, like you say optimal, but what if I choose something that is not so optimal? Is it very different? Like having a three-stage process, but not with really optimized pressure. Can you?
Yeah, you'll definitely see a difference. You'll be surprised when you do the exercise how different it can become. Yeah.
Is there a general rule in the industry how many places you use, or
How many stages?
how many stages?
It's generally between 3 and 5. You know, as a general rule. I mean, for bigger projects. And for bigger projects, what they often try to do is either create this extra natural gas liquid stream, or they actually just do a lot of natural gas processing. They put refrigerators on the gas streams, extract out liquids, and they try to get it, push it back into the oil without making the oil unstable. They do a lot of tricks to get it. You know, the factor's 20s. It's a big number. So they do a lot of things to get that. But the number of primary stages of separation is usually 3 to 5 for bigger projects. Well, if it's any consolation, I was in London the last 2 days doing work, and with a bunch of lawyers, and no, a couple of lawyers, and for, you know, I was, you know, looking forward to this nice dinner in London. You know, there's so many places to go and everything. You know, being paid by somebody else, and so as we're leaving the first day, they say, "Well, Curtis, you have your homework now." So I was doing exactly these kind of calculations, you know. So I had to eat fish and chips on the way home, work all evening, and then, you know, and they thought it was so cute, you know, that they were giving me the professor assignment. So, you know, it never gets old, but it's interesting stuff. It's non-intuitive. And so when you're doing it, at least you can think that, yeah, Curtis actually had to do it. But not only I had to do it in an evening and at the expense of my social life in London. So, you know, it could be worse than what you have. So, okay, so that's it.